So when we talk about solubility, we're talking about what dissolves. What types of solutes will dissolve in what types of solvents. Not everything dissolves into everything else. So if you know the phrase, oil does not mix with water, oil and water do not mix, that's because the two substances are, insoluble with each other. You can add as much oil to water as you want, or vice versa. They're not going to mix. They're just going to float in two separate layers. But if you take something like table salt or sugar, table salt and sugar, they're very soluble in water. They'll dissolve readily. But if you try taking table salt and putting oil, that's not soluble. Salt's not going to dissolve in oil. It'll just fall to the bottom. So, what makes things dissolve into each other? So what will dissolve in water? What will dissolve in a nonpolar or organic substance like oil? Well, that's where you get the term like dissolves like. The way something can be soluble in something else, or the way things will dissolve, is if they have similar intermolecular forces. So if the intermolecular forces and the structures of the solute and the solvent, if they're very similar, very compatible, then they'll mix. You'll get a solution. If not, it's not going to happen. Okay. So if you look here, I got two molecules. I have your water molecule on the left, and here, this is benzene. Okay, 6-carbon ring, couple double bonds there, C6H6. All right. So, now water is a hydrogen bonding. This is your negative end, and that's your positive end. So that's your polar molecule. And if we look at benzene, nope, not polar at all. Say this is a nonpolar, or this is an LDF intermolecular force, London dispersion forces. Okay. So let's say if you have something like sodium chloride, NaCl. Right, now they have to be similar in molecular forces. They don't have to be the same. Okay, so NaCl, that's ionic. Na is a positive ion, and chlorine is a negative ion. And when you take sodium chloride and you add it to water, well, when that sodium chloride comes in contact with the water molecules will actually pull apart the sodium and the chlorine. The chlorine will be attracted to the hydrogen end, and the sodium will be attracted to the oxygen end. Right? So that's what splits up the sodium chloride, and that's what makes your solution. That's what makes them dissolve. Right? Now with benzene, look at benzene, there's no positive ends or no negative ends, nothing strong enough to separate the sodium chloride. So it's not going to split apart, so it's going to stay a solid. Okay? It's not going to mix at all. Right? So let's look at something else here. Let's look at propane, CCC. This is a propane. This is a propane gas you burn. Cook your hamburgers and hot dogs. Alright, so what are the intermolecular forces here when I finish writing this? Alright, see a polarity there? Nope. None. So so propane is also LDF. So what do you think will dissolve this? What do you think it'll mix with? Yeah, it'll mix with the benzene. Okay, they're both carbon and hydrogen compounds, so it's similar in structure, similar in properties. They're both London dispersion forces, so they'll mix together well. Water molecules, with those positive ends and negative ends, they don't have anything to attach to on this propane molecule, so it's not going to work. So propane would dissolve in the benzene, but not the water. Now we're going to take this propane and we're going to tweak it a little bit. So I'm going to take off one of these hydrogens here, and we're going to add this OH. So that's that propane. This becomes propanol, also known as propyl alcohol. Now this is similar to the isopropyl alcohol that you have in your bathrooms, or in your bathroom sinks. This is another type of propanol molecule. What do you think this will dissolve in? Yeah, the most likely dissolve. This can actually now dissolve in water. Why? Because there's your hydrogen bonding area. Alright, so there you go. So dissolve in water because yeah, it's got the similar bonds. It's got the hydrogen bond with the hydrogen bond of water. So that's where you get your like dissolves like. Alright, so look at some other examples here. Here we have water, H2O, and carbon tetrabromide. So here's your iodine molecule, I2. So what do you think? We'll dissolve it. What will iodine dissolve into? Yes, iodine's LDF. Again, water is your hydrogen bonds. And CBr4, also LDF. And so, yeah, that'll be the winner there. Okay, carbon tetrabromide, that'll dissolve in that. Water, no. You take some iodine, put in water, it'll just sit to the bottom. Alright, so let's see what will dissolve in what here. Here I have a list of different solutes here. And here's your two solvents that you can choose from. Here we have water, H2O, and carbon tetrachloride. Alright, so we'll look at KCl. What do you think? Yeah, that'll be water. Alright, KCl dissolves in water because it's ionic. Got K plus, Cl minus. Alright, what about NH3? Alright, if you said water, you are correct. Yeah, because what's the intermolecular force for NH3? Alright, yeah, it's hydrogen bonds. If you sketch NH3, we'll sketch that out here. Yep, there's a shape. And yeah, that shows it's a hydrogen bond. There's your strong electronegative nitrogen and your hydrogen atoms. Alright, XEF4, what do you think? Yeah, that'd be CCl4. And yeah, you want to look at the shape there. So xenon. There's your 4Fs. Alright, does that look polar? Nah, it doesn't look polar. That's covalent bonding too. Yeah, CCl4. There you go. Alright, CH3COOH. That would actually be water. Alright, so let's check that out. If you probably have to look at the structure for this if you didn't want to sketch it out right off the top of your head. Here's your CH3, COOH. Alright, if you remember, that is acetic acid. Alright, so yeah, acetic acid, obviously that's vinegar, that's dissolves in water. Right? You have your negative oxygen here, you have your hydrogen bonding right there, so that's a pretty good polar molecule. So yes, water would be the one for that. Last but not least, yeah, this would be CCl4. Alright, because that's not polar at all. So there you go. Alright, here's a good question I found before. Alright, so this is, I got 3 different compounds here. We separate these. There's 1, there's 2, and there's 3. Alright, so this is called methanol. It's pretty soluble. Yeah, so this is very, okay, we call this very soluble. Alright, you got that strong bond, or that strong hydrogen bond there. Alright, what about this one? Yeah, that's ethanol. Alright, so yes, it is very soluble. Now let's look at this. Ooh, hey, well, I got that hydrogen bond there, so this has got to be soluble. Slightly soluble. So top 2, they'll dissolve really readily. All right, almost all you add to water, almost all this you add to water, it's going to dissolve. This one, very little is going to dissolve in water. All right, so why is that? I mean, you got the hydrogen bond there, shouldn't it? So what do you think? What do you think the reason it's not soluble, or very slightly soluble? That'd be this big area right here. All right. All right, this is a very large molecule. It's a large LDF area. All right, a lot of carbons and hydrogens. There are a lot of positives areas. The only way a water molecule, at least the hydrogen part of a water molecule, can attach is right here. Okay, small area for it to hook onto to dissolve. So it is slightly soluble because you have the hydrogen bond, but you just get this huge area, which is just a long carbon chain, and not really too readily soluble, so it won't dissolve as well. Alright, so here we talk about dissolving, especially dissolving ionic compounds. If you take something like NaCl, you want to dissolve in water. And what happens is the water molecules actually go up and attach and pull apart sodium ions and the chlorine ions. So since sodium forms a positive ion, it's a positive ion in the compound, it's going to be attracted to the oxygen end. Whereas a chlorine, which is negative, it's going to be attracted to the hydrogen end. So what you have here when you dissolve your sodium chloride, you're going to see sodium ions kind of hovering around the oxygen, and chlorine ions hovering around the hydrogen ions. So they're just attracted, positive and negatives, just as they should be. Get some seals here. Right. So that's why you talk about, you really don't have sodium chloride dissolved water. You just have sodium ions and chlorine ions floating around. Right. So now, not all positive and negative ions are alike. So what we have something that's called what are better hydrated or more soluble. In other words, some ions will dissolve a lot more readily than others based on their atomic structure. Okay, some are pretty straightforward to figure out, like this. All right, what do you think will dissolve better or have a greater attraction to a water molecule? So really, that's what you think about when you think of this. Which of these ions have a greater attraction towards a water molecule? Yep, most likely be oxygen. All right, why is that? Yeah, because of the -2 charge. All right, it's pretty easy. Here's your your water molecule. Okay, with that -2 charge, it's a really strong charge there. So that O2 minus charge is going to have a nice strong attraction towards that hydrogen atom in the water molecule. So you're going to hold on a lot tighter. So fluorine's still attracted, it's just not as strong of a hold there. That's what I mean by what's better hydrated. Oxygen has its stronger negative charge to be attracted more towards the hydrogen atom. It's going to hold on to it and stay dissolved, stay in the water as an ion. A lot easier than fluorine. Here's a couple other examples here. So, yeah, Mg plus 2, K plus 1. Right, yeah, just like last time. This thing will work better. Because you have your water molecule. Right, your +2 charge, stronger positive charge, is going to have a stronger attraction towards that towards the oxygen in that water molecule. All right, so now we're going to get a little tricky here. Let's look at this. All right, what's more attractive to the water molecule, fluorine or chlorine? If you said chlorine, you're right. And I'm going to rewrite the water molecule, make it easier to show. Because yeah, chlorine's going to attract to what part of the water? Yeah, chlorine's going to attract to the hydrogen atoms. All right, so chlorine's going to be a stronger attraction. And why is that? Really because it's, well, in one word, it's bigger. But again, that's not the exact explanation, so you can't just say it's bigger. You got more electron density. You got all these electrons around chlorine. Remember, chlorine's in the third energy level, so that's 3 energy levels worth of electrons. So all those electrons are going to have a much stronger charge in that hydrogen. Okay, fluorine just has 2 energy levels, and that's many electrons, not that strong of attachment to the water molecule. Alright, so well, let's check this out. Okay. Now, what part, magnesium and calcium, what part of the water molecule will that hook onto? Yeah, that'll be the oxygen, because oxygen's negative, and those ions up there, those are positive. So it's better hydrated there. Oh, calcium because it's bigger. Nope, wrong. It's the magnesium. That one wins out. And why does that win out? So magnesium's it. Because it is smaller. Alright. Yeah, it's chlorine's bigger, that should win. Okay, well, really, what's creating the positive charge of magnesium? Not the electrons, right? No, not the electrons, but the nucleus. Alright, the nucleus, and magnesium, after it loses its extra 2 electrons, just has those 2 energy levels. So that positive charge can get outside the nucleus a lot easier. And calcium, alright, calcium's in the third energy level, so that's got an extra energy level there. So that's a lot more shielding effect. Alright, so yeah, so positive ions, the better hydrated positive ions, those would be the smaller ones, because the nucleus is closer to the outside of the atom. That positive charge can get out and get attracted to the oxygen much better. Right? Whereas on the flip side, you go with the bigger negative ions, because that gives you more electrons, so that'll attract towards the hydrogen part of the water molecule. And we'll do one more example here. Let me have my slide that you might see. Here we have, we're going to do ClO4 minus and Cl minus. So which one's better there? That's the winner. Alright, first off, what part of the water molecule will those be attracted to? Yeah, attracted to hydrogen. Alright, so yeah, so be more attracted to hydrogen because you have these oxygens. Alright, got all those oxygens, very strong electronegative oxygen atoms. Alright, really pulling those electrons away from the chlorine, gives you a really strong negative charge. That's going to make a nice strong attachment there. Yeah, so you got the more oxygens, the more negative it's going to be, which means the more attractive it is to the water molecule. Alright, so just some examples of figuring out solubility, what's better hydrated or more soluble. And you just have to look at the structure and determine it that way.